Okay, this is lesson 13.7, using sampling to predict. In lesson 13.6, we learned that you can use the results of a survey to predict future events. In most cases, it's not realistic to survey every person in the population to be studied, so instead a smaller group or sample is chosen from the population. But in order for any predictions to be reasonably valid, we must be sure that the sample is unbiased. An unbiased sample has the following characteristics. It has to be representative of the larger population, which means, for example, if you wanted to generalize to, let's say, the entire school, you wouldn't go and survey just first graders because that wouldn't be representative of the entire student body. An unbiased sample also has to be selected at random or without preference, so you can't go out and survey your best friends or just girls or something like that. It has to be random. And an unbiased sample also has to be large enough to provide accurate data. So if you survey 3 people and then use that to generalize to 3,000 people, that clearly would not be valid either. So these are some types of unbiased samples. You have a simple random sample, which is pretty much exactly what it sounds like. Each item or person in a population is as likely to be chosen as any other. Some examples would be if, say, 30 student ID numbers are randomly selected by a computer. That would be a simple random sample. A stratified random sample is also random, but in this case, a population is divided into similar non-overlapping groups, and then a simple random sample is chosen from each group. So that would be like if you were surveying the school, um, the school population is clearly divided into grades. So if you just did a simple random sample from each grade, that would be a stratified random sample. Or, in this example on your notes, a population of election districts can be separated into urban, suburban, and rural strata. So from each of those sections, you could survey a random sample of people. And then a systematic random sample is where items or people are selected according to a specific time or item interval. So every 20 minutes a customer is chosen, or every 10th customer in line is chosen. It's systematic. It's the same time interval or the same item interval for each thing or person that is surveyed or chosen. A sample that is not representative of the population is called a biased sample. A biased sample usually favors certain parts of the population over others. So these are two types of biased samples. A convenience sample includes members of the population that are easily accessed. So for example, the first 10 students in the cafeteria line. Well, it's clearly biased because you can't say that those first 10 students are representative of the entire population. Um, those first 10 students might be exceptionally hungry, and that may be why they were in line first. That's just a convenient 10 people to choose, but that's not actually random. And then the second type of bias sample is a voluntary response sample. So that involves only those who want to or can participate in the sampling. So anything where you give a survey to everybody and then just use the ones that are returned because they're voluntary. So for example, the principal sent an email to graduating seniors asking them where to hold commencement. Seniors are asked to vote through an online poll. Clearly here, the only people's opinions who are going to be included in this poll are the people who want their opinions to be included. It's not every single senior going online to vote, and it's not a random sample of seniors either. It's the seniors who most likely have the most vocal opinions about where to hold commencement, and that's not necessarily representative of the whole population. Okay, so let's take a look at the first example. This says a hardware store wants feedback on its products and service. The store includes a telephone number on each receipt so customers can call and participate in a survey. We want to first identify the sample as biased or unbiased and then describe its type. Okay, well in this case, there's a telephone number on the receipt so customers can call and participate in a survey. So the only people participating in the survey are people who decide that they want to call the number on their receipt and participate. So this would be an example of a biased sample because it is a voluntary response sample. because the only people participating are the ones who want to participate. So that would be biased. All right, example 2 says, to determine the popularity of a political candidate, 5 people are randomly polled from 10 different age groups of eligible voters. Identify the sample as biased or unbiased and describe its type. Okay, so already here we're seeing the word randomly, which sounds really good because any of the unbiased sample types have to be random samples. Well, we have 5 people randomly polled from 10 different age groups. So we're talking about population that's already been split into separate groups, 10 different age groups, and then 5 people chosen from each group at random. So that would be an unbiased sample, and it would be an example of a stratified random sample because the population is divided into similar non-overlapping groups. In this case, it's age groups. So we would say that this is unbiased, and the type is a stratified random sample. Okay, at the top of the next page, there are 2 try it yourself problems for you to do on your own. It's the same types of questions. You're just determining whether the sample is biased or unbiased and determining what type it is. So go ahead and pause the video and answer those 2 questions. When you're ready to check your answers, press play. Okay, this first one is a biased sample because it is a convenience sample. The only people being surveyed are not truly chosen at random. They're chosen because they are a convenient group of people, the members of the math club. That's not random, and you're not going to be able to generalize to students in general when you're polling the math club. So this is just a sample that's convenient because the math club, you know, if you go while they're meeting or something like that, they're right there. You can just poll a group of people and hey, there we have our sample. That does not work. That's biased. All right, and for 2A, this is unbiased. And this is a systematic random sample because there's a system, there's a pattern for how the sample is chosen. It's every 8th person. So since that's a set interval, that's a systematic random sample. Okay, if data is collected from an unbiased sample, we can usually use this data to make predictions about the characteristics of larger populations. So look at example 3. It says to determine the number of first-time visitors to a mall, every 15th shopper to enter the mall was polled. There were 3,000 total shoppers in the mall, and of the shoppers polled, 26 shoppers were in the mall for the first time. Is the sampling method valid? If so, about how many of the 3,000 shoppers were in the mall for the first time? Okay, so the first question is still asking us the same thing. Is this sampling method valid? Well, if we look at what happened, as people came into the mall, every 15th shopper was polled. So there's no preference given to any particular types of shoppers or anything like that. This would be another example of a systematic random sample because there's a set interval to which shoppers are polled. So is this method valid? Yes, it is valid. And again, that's because it's a systematic random sample. Well, if it's valid, then we can use that to predict what, since the sample is supposed to be roughly representative of the population, we can use that to predict what the proportion would be in the population. So first of all, we need to know how many shoppers were surveyed. So every 15th shopper was polled, and there were 3,000 total shoppers in the mall. So if I divided the 3,000 by 15, because out of every 15 people, 1 person was polled, this would give me the total number of people polled. And if we divide this, this comes out to 200. And of those shoppers polled, 26 were in the mall for the first time. So 26 out of 200 were in the mall for the first time. We want to generalize this to some number of people out of 3,000 shoppers. So 26 out of 200 that were surveyed said they were in the mall for the first time. We want to know how many people out of the 3,000 total were in the mall for the first time. Well, we've got a proportion here, so we'll cross multiply, and we get 200x equals 78,000, and then we'll divide both sides by 200. So we get x equals 390. So about how many of the 3,000 shoppers were in the mall for the first time? About 390. Okay, let's look at example 4. It says a magazine publisher mailed a survey to its subscribers to find out how many plan on renewing their subscriptions this year. 200 people responded that they would renew their subscriptions. Is the sampling method valid? If so, about how many of the 8,000 subscribers will renew their subscriptions this year? Okay, so in this case, we have a survey that was mailed to subscribers, and then people choose to respond. So this is not a valid sampling method because it's a voluntary response sample. People are choosing whether they respond or not. They're not selected at random. They end up being selected based on their willingness to participate. So we would say no, it is not valid. Okay, there are 2 try it yourself problems at the bottom of the page. You're basically doing the same thing. So go ahead and pause the video, answer those questions, and when you're ready to check your answers, press play. Okay, for the first one, is this an accurate sampling method? No, it is not accurate. And again, this one is also a voluntary response sample. So 100 customers were given surveys, but only 40 of them returned their survey. So the only people that are likely to return the survey are people who had an exceptionally good experience or an exceptionally bad experience. Regardless, any sort of voluntary response sample will always be considered biased. So this is not an accurate method. So we won't be able to tell how many customers had a bad experience. For 4A, this one is valid. Because it's a systematic random sample. Every 5th person was surveyed. So we should have been able to set up a proportion there to find out how many people of the 380 people who dined at the restaurant ate dessert. And you should end up with 228 people. Okay, so that's it for lesson 13.7. We're going to move on to 13.8, which is counting outcomes. A tree diagram is a visual display used to find the number of outcomes given a number of choices. So in section 13.6, one of the things that we did was to create a table of the sample space. So if you recall, there was one in your notes where you had 2 number cubes that were rolled. So you created a table of each of those matchups. There was one in your homework where 2 spinners were spun, where you had 4 numbers on each one and you created a table of the sample space, all the pairs of outcomes. A tree diagram is another way to represent those different outcomes, but this works really well if there's more than 2 choices as well, because you can extend your tree diagram as long as you need to. So let's take a look at what a tree diagram looks like in the first example. It says how many different combinations of beverage and bread can be made from 3 beverage choices, coffee, tea, and juice, and 3 bread choices, bagel, muffin, and scone. Draw a tree diagram to find the number of different combinations. Okay, well, the first thing you can choose is a beverage. So, and there are 3 options. So we either choose coffee, or we choose tea, or we choose juice. And these are all the beverage options. Now from there, for each of these 3 beverage choices, you also have 3 bread choices. So let's say somebody were to choose coffee. Well, they're still free to choose either a bagel, a muffin, or a scone. Same thing with tea. Once a person has chosen tea for their beverage, for their bread they can choose a bagel, a muffin, or a scone. And of course the same thing for juice. You have the option of a bagel, a muffin, or a scone. Okay, and each of these are bread options. So the actual outcomes for each of these. For this top one, you have coffee followed by a bagel. So this is coffee and a bagel. The second one is coffee and a muffin. And then coffee and a scone. And the same thing for each of these. So tea and a bagel, tea and a muffin, or tea and a scone. And then same for juice. Juice and a bagel, juice and a muffin, or a juice and a scone. Okay. So each of these represent a different combination of beverage and bagel. And we notice we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So all of these represent 9 possible outcomes. Okay. So for try it yourself number 1, you're going to do the same thing. A closet contains a red top, a blue top, and a white top, and pants and a skirt. So you're going to use a tree diagram to find the number of outcomes. And the outcomes here would be different outfits. So different ways to combine a top with one bottom, either pants or the skirt. Okay, so go ahead and pause the video, create the tree diagram to find the number of outcomes for this problem, and when you're ready to check your answers, press play. Okay. For this, since you should just be checking your answer, I'm going to kind of shorten my things here. This is a red top, blue top, white top, and this would be pants, skirt. So then in each of these, this one is a red top with pants, this is a red top with skirt, blue top with pants, blue top with skirt, white top with pants, white top with skirt. And from here you can see 1, 2, 3, 4, 5, 6 outcomes. Okay. Another method that relates the number of outcomes to the number of choices is the fundamental counting principle. Because let's face it, I'm guessing most of you do not want to have to create a tree diagram every single time that we need to know how many outcomes there are in a given um, set of events. So we use the fundamental counting principle, which says that if event M can occur in M ways and is followed by event N that can occur in N ways, then the event M followed by N can occur m times n ways. So this just says if you have something that has a certain number of outcomes and you have another event that follows it that has some other number of outcomes, to find how many outcomes there are for the two events combined, we just multiply those two numbers. So if we were to apply that to each of these examples that we did, here we have 3 options for a top and 2 options for bottoms. 3 times 2 would give us 6. And then for the first example, we had 3 choices of beverage and 3 choices of bread. 3 times 3 gave us 9. So this allows us, if all we need to know is how many outcomes there are, this allows us to bypass the tree diagram and answer that directly. So let's look at example 2. It says a cell phone company offers 3 payment plans, 4 styles of phones, and 6 decorative phone cases. How many phone options are available? Well, in this case, we have 3 different types of events. We have a payment plan, we have style of phone, and then decorative phone cases. Okay, so for the payment plan, there are 3 possible options. For the phone, there are 4, and for the case, there are 6. So how many phone options are available? How many combinations of these numbers of things are available? Well, we just multiply. So 3 times 4 is 12, times 6 is 72. So this means that there are 72 options. Okay. At the top of the next page, there is a try it yourself problem for you to do on your own using the fundamental counting principle. So go ahead and pause the video and answer that question, part A and part B. And when you're ready to check your answers, press play. Okay, for the first one, the total number of outcomes, you should have gotten 312. And for the total number of outcomes for the second one, you should have gotten 260. Okay, when you know the number of outcomes, you can find the probability that an event will occur. Because remember, probability is just the number of favorable outcomes over the total number of outcomes. So if we can find the number of outcomes, we can find the probability that an event will occur. So let's look at example 3. It says an ice cream parlor has a special where you can build your own sundae for $3. You are given a choice of chocolate, vanilla, or strawberry ice cream, sprinkles or nuts, and chocolate or caramel topping. What is the probability of randomly selecting vanilla ice cream with nuts and either chocolate or caramel topping? Okay, so here we have 3 different choices to make. There's the type of ice cream, and we have 3 choices for that: chocolate, vanilla, or strawberry. After that, we also have the choice between sprinkles or nuts, and that is sprinkles or nuts is 2 choices. And then the different toppings, chocolate or caramel topping. And since that's just chocolate or caramel, there are 2 possible options there. So total, there are 3 times 2 times 2. 3 times 2 is 6, times 2 is 12. This is 12 possible outcomes. Well, if I want to find the probability of randomly selecting vanilla ice cream with nuts and either chocolate or caramel topping, I now, for this to happen, I now don't have 3 choices of ice cream. I would have to choose vanilla, so I only have 1 choice. Sprinkles or nuts? Well, we want to know the probability of selecting vanilla ice cream with nuts. So again, just 1 single choice here. But then for topping, either chocolate or caramel topping. Well, there were only 2 choices for topping anyway, so we'll take a look at both of those, chocolate or caramel. Okay, so the number of favorable outcomes would be 1 times 1 times 2, which of course is 2. So 2 favorable outcomes. And the probability is the number of favorable outcomes over the possible outcomes. So 2 over 12, which of course reduces to 1 over 6. Or if you change this to a decimal and then to a percent, it's 16 and 2/3%. Okay. So at the bottom of the page, there are 2 try-it-yourself problems for you to do on your own. So go ahead and pause the video, answer those questions, and when you're ready to check your answers, press play. Okay, for this one, the probability that all 3 will be left turns, you should have gotten 1/8 or 12.5%. And then for the last one, the probability that he will roll a 3 and toss heads, you should have gotten 1/12 or 8 1/3%.